I'm Naoki Masuda from the University of Bristol, and in this next lecture, it should be like on 1 hour. So I would like to introduce topics of the random walks and diffusion networks. So in the first hour, we spent to a introduction and the relatively theoretical stuffs. And the second lecture, we said about several of the applications. Okay. So let's start the first part, with first hour. So diffusion is a very broad term, but it's one of the pioneer of this diffusion and also random walks is the Einstein. So perhaps many of you know. So he looked at the Brownian motions, and this is of course a type of the random walk, and there are various pioneers of random walks. I'm not talking about the random walks on networks here, but the random walks in general. So that term was coined by Pearson, famous for, of course, the Pearson correlation coefficient, and Gambler's ruin was a very classical topic in mathematics in a way before the early 20th century. So it has a long history. And it has, been studied in mathematics and also neuroscience and studies of physics and computer science and many other fields. And interestingly, random walks have many applications to model the phenomena, also to random walks are applied to development of various algorithms to mine information from data, let's say. So if you look at the mathematical or literature books, I mean, it probably starts off from what random walk model is. But so here I want to ponder a bit on why we study this. So the first thing, so we study random walks, particularly on networks in this lecture, and in this field is of theoretical interest. So classically, let's say the random walks have been studied in one-dimensional space. Either discrete or continuous. So what would happen if we study the same object on networks? And another important thing for studying random walks on networks is that they have enjoyed a lot of applications, as written here. Okay, so this one allows for me to write something, draw something. So so there are many applications, some of which I am going to touch upon in the next lecture actually. So before going to networks, let me start from the one-dimensional, random walks to warm me up. Okay, so let's assume in a continuous space. The analysis of a discrete space case is similar. And in this lecture, critically, we distinguish between the discrete time random walks and the continuous time ones. But for here, for expository purposes, let's focus on random walks in discrete time. So the walker makes a step from one point to another in each discrete time step. So let's say the walker moves to an small interval, where this delta R is a small quantity with a certain probability in each time step. Then the master equation, which describes how the density of random walks, if there are many random walkers, evolves, is given by this. Okay. Can we decipher this? Okay, so this is time n-1. This is time n. And x prime is the previous position of random walker. And this corner, so-called, of course there are various forms. But here I am assuming that the new position x and old position x prime. And the probability that the walker moves from x prime to x only depends on the distance between the two. Okay, that's why this form happens. Cool. I mean, the possibilities, f function may have a Gaussian like form, for example. Okay, then in this way, so because to reach x from at time n, it could come from somewhere in the one-dimensional space, which we don't care. So if we integrate the equation with respect to somewhere, which is x prime, so we get this. Okay. And the theory has shown that the if f of is over say very how can I say the relatively benign form. So as time tends to infinity, so that this say density approaches the asymptotical approaches the Gaussian distribution, where the v so the mean position is, if you read this, so it's the peak of the Gaussian, so Vn, n is time, so it makes sense. So mean position, yes, evolves over time. Sorry. I don't think this is correct. This shouldn't be, say, proportion to n. Oh, yeah, right. So this is correct. Okay, so the square root is the say, mean displacement in say one discrete time. So if we repeat the same time, this is the mean displacement, and this is the mean say standard deviation. So this why mean moves say the peak of this density moves at a constant speed unless v is equal to 0, and then with some say width which is specified by d, which diverges over time because of this n term. Okay. So I don't show any derivation of this, but this is the consequence. And what about this continuous time? What is the continuous time random walk? So this is a very the introductory primer to the say the one-dimensional classical random walk in discrete time. And the instead of say the digging in more about say discrete time random walk in the one dimension, so I want to switch to continuous time random walk. So it is defined as follows. So there are relatively, I think, say few little just compared to discrete time random walks on as compared to say continuous time ones. But anyways, so the in the continuous time random walk, we wait for some time, continuous time, let's say, specified by this time length. Here's time axis, so the time flows in this way. So after waiting some time, which is usually determined stochastically, then at time t1, the walker hops from the current position to the next position. Here, so for the expository purposes, I assume that the space is discrete, so integers. So okay, it starts from 3, and then it decides to go down one step to go to the position 2 at time t1. And then after some time, so again, so there is an event issued, and then this time, so the walker decided to go up by one step to return to original position. This way we continue on. So we have to clearly distinguish between the two notions of time. One is a continuous time, physical time, and another is a number of steps. Okay, here is the first step, and here is second step, third step, and so forth, right? So the if we look at the number of steps and the corresponding position, this is the discrete time random walk. On top of that, the continuous time random walk specifies when it jumps, right? So how shall we analyze this system? So okay, so the analysis is sort of similar to the case of discrete time random walk. So now, so we want to also understand time. So the time at time t. So we want to know the probability p that the random walker visits position x, right? And to do this, random walker starting from the initial position at time 0, random walker has experienced n steps, and thus has reached x. And how many steps the random walker has had by time t depends, right, stochastically. So here, P of nt is the probability that the random walker has experienced n steps. I'm not asking, when we are talking about this density, say probability. So we are not asking, say, where the random walker is. And of course, depending on the assumptions, we can calculate or cannot calculate perhaps this probability. And usually, so they say the most commonly the assumption is that the events are issued according to the Poisson process. So the Poisson process means that the next event, time to the next event, obeys an exponential distribution independently for different events at rate beta. So in this case, the mean waiting time to the next event is 1 over beta. And the number of steps, of course, would be large if the mean time to the next event is small. So this is a very simple formula. So time t, this is the mean time, right, the denominator. So it's quite straightforward. So in this case, we can explicitly calculate the this distribution, how many jumps a walker has had at time t. This is a Poisson distribution. This is something you would learn in, say, probability theory undergrad course, I would say. Okay, this describes this P n of x n t part. And the P x n part is or has already been derived for the discrete time random walk. So this part doesn't necessitate continuous time. So discrete time random walks analysis uses the probability that the x so the walker visits position x given there have been n steps, right? So this is something we know from, say, discrete time random walk. So if you combine these two components, we can understand the behavior of the continuous time random walk. And the full solution is available in terms of Laplace and Fourier transform. So essentially, we analyze this one further depending on the, say, shapes of, say, P and 2P's, and, say, in terms of the, say, frequency domain, both in the sense of the space and the time, right? Space is Fourier transformed and time is Laplace transformed. It's all the interesting thing, but I'm not getting into it too much because I want to make this lecture the random walks on networks lecture. So let's start to talk about networks. Okay, so what's the random walks on networks? Okay, let me draw a picture. So this is a blank slide intentionally. So okay, I want to draw something to visualize what the random walk would be. Okay, let's say we have this network, whatever network, and then random walker visits either of the node in each, say, let's say, time step. So if the walker is here at, let's say, t equal to 0, the next thing we do is to select which node the walker is visiting in the next time step. So let's say, for simplicity for now, we assume that this network is undirected. There is no arrow. So if there is arrow, this we say directed. But here we are not assuming directed networks, but we do assume undirected networks where we don't distinguish the direction of the edge. Okay, so then if we do so, okay, this node has so-called degree 4. Degree is the number of edges connected to the node. And then in the model, which we consider, I think, throughout this lecture, and the next is called a simple random walk. Okay, so by definition, it chooses one of the 4 destinations, either this one, this one, this one, or this one, with equal probability, which is 1/4. And if one edge is, let's say, thicker than others, let's say, and if it is twice thicker, we assign edge weight like this. In this case, the edge weight sums up to, say, by convention, let me use the term node strength. It's essentially, or the equivalent to the weighted degree is equal to 5. Okay, this summation of 1 to 1, 1. And this edge is chosen with probability 2/5, and this edge 1/5 in this way. Okay, so let's say anyway. So according to this probability, we assume that okay. So let's say this edge has been chosen, and then the random walker moves to this new node at time 1. So we are now assuming for simplicity discrete time random walk, right? And then again, so if you count the number of edges, it's 6. Okay, but the edges might be weighted, but for simplicity, we assume that there is no weighting. In with the probability of 1/6 for each edge, we select which edge to be passed in the next time step. If this edge is chosen, okay, so the random walker goes to the next node like this. And let's say if this wedge is chosen with probability 1/3, it comes here. Interestingly, so here there is only one edge right out. So with the probability 1/1, which is 1, the random walker has to move back to this node. In this way, we continue the walk. This is the model we consider in this lecture mostly. So how shall we analyze this? So the we not necessarily not just for the random walks. We often use this adjacency. Very often use the adjacency matrix, which is a matrix representation of the matrix. It's not that difficult. If you are given this network, it is equivalent to this matrix 5x5 matrix. So it has entry 1 in off diagonal where there is an edge. So if they say node 1, say this is the first and this is the second, right? Column on the first row. Because I mean these two are adjacent by an edge. So there is an edge between nodes 1 and 2. There is one here, okay? Likewise, so there is one again here between 1 and 3 because there is an edge here, right? But if you look at, let's say, 2, 3, it is equal to 0 because there is no edge between 2 and 3. There is no edge, okay? And by convention, of course, it depends on the application, but let's say we have, let's say, 0 on the diagonals. And this representation can allow directed, weighted edges as well. So if the edges are weighted, so the numbers rather than 1 can appear here. If the network is directed, then the this matrix becomes asymmetric. So the symmetric matrices, adjacent matrices, imply that the network is undirected. Okay. So how shall we define and analyze? Start analyze this the random walk. So to use this, so that we have to introduce first the transition probability matrix. So we have to understand the probability with which the walker moves from. So okay, so let's say we start from discrete time random walk. So we want to understand the probability that this event happens. The walker moves from node I to node J. Okay, as I showed in the visualization, the probability is this. What's this? Okay. At I, so this one, the denominator counts the number of outgoing edges. So in the figure I drew, I didn't distinguish between incoming and outgoing edges because the edges are assumed to be undirected. But in case the edges are directed, right, like this, okay. So walker visiting at node I could go to J or K, but it can't go to L because L sends and directed edge to I, but not vice versa, right? So if the walker is here, node I, then it has to to determine the next step. We have to first calculate which nodes are downstream. Which node receive downstream to node I, or which nodes receive edges from I. So this is here. So by convention, Aij means that there is an edge from I to J. Some people use an opposite the convention, Aji. But in this lecture, so we consistently use this notion. That's first thing. So if there is no edge from I to j, so we can't go from I to j in one step at least. So this represents this, say aij. And SI is a normalization actually, so it counts the number of edges from I to j. So in this way, this is a probability. And this representation also accounts for the case where the networks are weighted. So even if we insert the numbers rather than 1 into aij, it works. So in this way, so this representation allows directed networks and weighted networks. But practically, which complicates things, either directed networks or weighted networks more than the other. So in practice, so when we make things from unweighted networks to, it's not just for the random walks, but the various network analysis, network science analysis. So if we make things from unweighted networks, okay, if you have derived some, say, mathematical formula or the whatever analytical results, particularly, which have been established for unweighted networks, then of course there are many exceptions, but by and large, so it tends to be the case that this extension to the case of, say, weighted networks is relatively easy, and it is the case for random walks. But if we have derived something for undirected networks and try to extend the results to directed networks, it's usually difficult. So the weights are easy, directions are difficult. There is no mathematical proof for this, but this is our rule of thumb, I would say. Anyway, so if we're given, okay, so this is our say test network, 8 nodes, many edges, I haven't counted. And then this is a adjacency matrix. Just note that the adjacency matrix is now asymmetric. Let's say if you look at 2, 4, here it's 1, but 4, 2 is 0. So if you inspect these two vertices, yes, indeed, there is an edge from 2 to 4, but not vice versa, right? So this is consistent with the picture. And then if you use this normalization, so we get an so-called transition probability matrix, which is this. We divided elements of, say, the adjacency matrix by the so-called out strength. If the network is undirected, it is called out degree. But anyways, this is the case. Okay, so the important things to note here is if you sum up the numbers, perhaps the slides are basically bluish, so let me switch to red. The sum is equal to 1, right? If you look at whatever row, this is the case, sum is 1, right? And it represents the fact that the walker, which is currently visiting node I, should go somewhere, in the next time step. Okay, somewhere here means either node 3, node 4, node 8. Okay, this part I think I explained. And conservation explains, so the I goes somewhere in the next time step. Sometimes we allow self-loop, meaning I goes to I, like this. In this case, as opposed to what I've said before, so we are allowing self-edge, so the adjacency matrix have a diagonal term, let's say something, which is non-zero. And then it leads to the positive probability. So of course this is positive usually. So okay, positive probability of going from I to I in one step. But this is fine. With this case being included, this conservation always happens. We say conservation because the density of the random walkers is conserved. The walkers don't disappear anywhere. Walkers don't emerge from anywhere. If you look at the entirety of them, of course walkers would emerge from other nodes, because walkers are moving. But if we think about the entire network, if there are, let's say, 3 walkers in the beginning, the number of walkers stays 3 whatever time we run the random walk. Okay. Next step, dynamics. So this is the Markov chain actually. So this equation describes the evolution of the probability where the pi of n is a probability that the node I is visited at time nth step. So this equation connects that probability at time n with the same probability at time n plus 1. So let's decipher this. This is something, I mean, similar to what I have covered in the one-dimensional case in the previous slide, right? So the for a walker to reach node j at time n plus 1, it has to come from somewhere. So okay, let's say it is visiting I at node n, and of course the walker has to travel from node I to node j in one step. But importantly, to calculate this quantity, the probability that the walker visits j at time t plus 1, it doesn't matter where the walker comes from. So that's why we took a summation over I, right? And in this way, so we can assure that, or can say, check that if okay, this is satisfied. Show that. I'm saying that it's show. Okay, this is a lecture, so it's not really to, describe my own research too much. So it's a pedagogical, and I want to introduce beginners, particularly to these topics. So let's try to show this. Okay, I'm asking to show that walker is conserved. So walker density is normalized to 1, okay? And if this holds at time n, any time n, let's say initially, so it holds in the next time step. So let me show this. Okay, we want to prove the following. Okay, let's sum it over all the nodes. So this should be equal to 1 if the walker doesn't disappear. Walkers, let's say there are many walkers whose densities we're discussing. Let's say, and if the walkers don't disappear or emerge from anywhere, if we sum density or the probability over all the nodes, it should be 1. If it was 1 in the previous step, that's what I'm sure. Okay, do we know what this quantity is? Right, because of this relationship. We have this, okay, hopefully. And it is convenient to sum over j first. This one doesn't contain, okay, so let me go step by step, I think. So exchange the order of the summation. Right? And this is also can be taken out here because it doesn't contain j. And if you look at this, okay, let me just write it again. A bit verbose, but for those who don't know the topic, it will be nice. Okay, and this is a probability that I goes somewhere. And I'm set here, so it's the sum is equal to 1, so this one becomes 1. Okay, we have proven. Okay, the walker's probability summed over all the nodes at time n plus 1 is the same as the when the time was n. Okay, so if we use this logic, okay, the sum is of course equal to n minus 1, etc. So it's conserved. I should distinguish between small n, which is time, and large n, which is the number of nodes. Okay. So this is assumption. We start from the uniform density, so some density distribution of random walkers at time 0. Okay. With vectors, this is the equation of the evolution dynamics. This is the same. Okay, here's a convention. This is a vector representing which node the random walker is visiting at time n, and this is a row vector, horizontal vector, and this is also horizontal vector, and this is a matrix. Fine. So if we recursively use this relationship, okay, so we can fathom that this is okay, the Pn. If we shift n by small n by 1, okay, perhaps I should use the vector like this, right? And this also tells what happens between two steps this way. So if you iterate this, we get this. Okay, this is actually everything. about the random walk in a sense. Because if we have the initial condition, and this evolution operator t, and we multiply this matrix n times, we get an density of random walkers at time n. Okay. So question here to the audience: so is this system linear or non-linear? Yes, it is linear, because I mean linear in everything. So this makes the system. So if the nonlinear would mean that okay, so p times p. Of course, p is a vector, so this operation is not allowed. So but let's say if the inner products matters or some log, of course, I mean it's a vector, so we have to be careful. But anyways, if there is a nonlinear say dependence or equation, so the system becomes nonlinear. But this evolution equation is really linear, which makes the analysis of random walks fairly easy. Of course, it depends on what you do. So if we talk about the very complex structure of networks, the analysis nevertheless becomes difficult. But anyway, so this is relatively easy. So that's why random walks, I think, have found many applications and many analytical results. Okay. So what shall we do? So what we have set up is the same random walks and the evolution equations. And if you look at the various literature on random walks on networks, the main things I think people have been doing are threefold within the theoretical domains. Of course, there are many other things as well here. The first three things, if I am asked to point out the first three tasks people do in analyzing, say, random walks and networks, are these three: stationary density, after infinite time, so where the random walkers would be; relaxation time, how does the random walker, or this density of random walkers, approach the stationary density as the time goes, well, very large, asymptotically. And the first passage time is more finite time behavior. So if this walker starts from I and try to reach J, which are not necessarily adjacent, say next to the I, then how many steps it requires? This lecture is based on the review paper which I've written, which will be mentioned in the very last part of the second lecture at least, or in this slide, at the end of this slide set. But anyway, so that review paper covers all these three topics, but in this lecture I'll focus on the first two, which are shown in red. Okay. So stationary density. Okay, this the first two equations are what we have, right? So it describes everything, in a sense, right? And if we wait for a sufficiently long time, this is the limit, and it converges. Well, of course, there are some rare cases it doesn't converge. But if it converges, then let's say it converges to pi asterisk, sorry. If this is the case, if we start from here, in a large time, this is vector. Okay, so just recap that this was the shorthand of the probability that the walker is a vector, right? So it's visiting each node. And in large time, so this converges to the stationary density, so-called. So if we plug the stationary density to both sides, P of n plus 1 and P of n, then we get this. And if we look at this equation as a linear algebra, matrix algebra equation, we can say that this, okay, the stationary density is a left eigenvector, yes, it is left, of matrix T with eigenvalue 1. Or this should be italicized. Anyways. Right? And the corresponding right eigenvalue, vector, sorry, is 1, all 1. Is it? Okay, let's discover this. Okay. So let T 1. What is this? 1. Okay, so perhaps it should be nicer to write this all 1 vector. I'm now assessing whether this particular vector is a right eigenvector of T matrix with eigenvalue 1. Okay. So okay, so if you look at the first row, the summation would be like this. Right? And second row would be, same j1 to n t2j times 1, because this is 1, etc. But I said before, so this is equal to 1. So the worker starting from I goes somewhere in next time step. So this quantity is equal to 1. And likewise, so the worker starting from 2, node 2, would go somewhere in the next time step, including itself, 2, node 2. So it becomes 1. Okay, and if you compare the left and right hand side in the vector form, we can say this. Here, the vector 1, say both 1 is say vector in a dimensional vector having 1 in all elements. Okay, if you look at this, okay, so we can say, okay, this one vector is a right eigenvector of t, and the corresponding eigenvalue is equal to 1. Okay, found this. Okay, the important thing is that, okay, if there is a right eigenvector, there should be a corresponding left eigenvector of the same eigenvalue, right? So which is this p. And here is a very central, I would say, result on random walks on networks. For undirected networks, so if there is no direction in the edge, the stationary density of, say, discrete time random walks, is given by this. What is this? Degree, essentially. So S is the strength weighted degree. So the convention was, okay, like this. If there is no edge, weight, we say that this SI is equal to 4, sorry. And if there is some edge weighting, so we take into account these values to say that SI is equal to sum of this, which is 7.5, right? So if the node has a large degree or the weighted degree, SI, we usually think that by the first approximation, this node may be important. And it is often called hub in network. Okay, so the hub might attract the random walks, and this theorem is saying that this is the case in undirected network. Okay, so let's prove this. Okay, what shall we do is to use this. Because this is the equation we want to solve. So this specifies the station density, right? So let's pretend that we know the answer, and to let's show that this solution, which is a solution, is consistent with this equation. Okay. Okay, let's do this. So, okay, fine. Right hand side. Okay, pj star asterisk, or is it tji? And okay, let's say we know that this is proportional to the weighted degree. And Tij, what about this? So if you remember from the past part, it was the Sj out and Aj. But here, I'm not discriminating between incoming edges and outgoing edges. So this is simply equal to Sj, node strength, how many connections, weighted connections, how much weight in total connection it has. Node has, okay? And we can cancel out these two things. And okay, let me just write down everything. But here I notice that This is just weighted degree again. Okay, the denominator doesn't involve j, so this is just constant. And if you look at the denominator, okay, so this the number of the weighted edges which comes into j, right, from some nodes I, sorry, j. But so this network is undirected, as I have written here. This is simply Si. So in this way, we have recovered this one. I mean, assuming that this one is given by this one. So this solution is consistent with the equation specifying determining the equilibrium density. So of course, we might ask a uniqueness of a solution, etc. But say this is a elementary lecture, so let's not ask it. So this proves this is the case. Is it fun? Yes, it is. So what's the meaning of this? So this is a bit surprising result. So I first learned this many years ago, so I was a bit surprised. I said, why? So let's draw a network. Oops, let's go back to, yeah, okay, so I basically, so I admitted I stay in the red. One, two, three, 4, 5, 6, 7, 8. Okay, let's say 10. This one has degree 10. And let's say that there are some remote places in network where they say different nodes have degree 10. And network is very large, so there are many nodes anywhere, right, within respective number of edges. Network drawing in this way is sometimes very deceptive, right? So it depends, this perception of our networks depends on how we draw networks in, let's say, the two-dimensional space. So it's a bit deceptive, but let's say we assume that, say, the picture for now. Okay, those who are, say, close to, say, this around here, so they are more maybe central. And this half is half because it has a large degree, but maybe provincial because it located very far from the center of the network. But I haven't defined what center means, so it's a bit controversial. But anyways, let's take this view. And then the theorem, which is this, theorem, okay, sets that the stationary density where the walker visits after sufficient long time only depends on the degree. So the large degree means that the walker would visit that node more often, right? And this has degree 10, and this also has degree 10. But this may be more central in some sense than the other, say, provincial hub. And also, if you look at the local connectivity, let's say how many triangles exist, say, in the neighborhood of this node, or many other various properties, these two nodes will be very different. For example, how many second neighbors, how many nodes there are, say, within 2 steps, not just 1 step. So this might have, say, 100, this might have only 15. But regardless of such differences, the theorem is saying that, say, the walker spends the same time on these two magenta nodes. It sounds a bit, surprising to me, because I mean, naively thinking, so that I might expect that this walker would spend less time on, say, provincial hubs rather than central hubs, whereas they say the notion of centrality depends on the definition. But the theorem says that it is not the case, okay? So the many things about this random walks theory algorithms use this fact that the stationary density is proportional to its weighted degree. How about the case of the directed networks? There is no such handy results. But we can guess something by the first order approximation. So what's this? Okay, this is correct, exact, rigorous. But if we admit that the how can I say, the stationary density of the let's say the neighbor may be similar between the neighbors, or which is not necessarily the case, but this is a first order approximation. And likewise, let's say out degree of the neighbor may be similar across different j's. If you admit this, okay, we admit this, we just eliminate dependence on this, which is totally untrue, but this is a first order approximation to replace this by constant. And then what matters, only matters is this summation, which is in degree, number of edges incoming to I. So within this approximation, naive approximation, so the probability that the walker visits vertex I is proportional to its in degree. This is intuitive, so because if say the I has many incoming neighbors, say many neighbors which send links edges to say node I, so it means that so there are many pathways through which the walkers enter I than otherwise. So it makes sense, right? But this approximation is accurate, indeed accurate in many empirical directed networks. But also other literature show that this approximation is very inaccurate in many other empirical networks. But intuition is very clear. But but we come back to this topic when you say page rank, which is I think the topic of the lecture 2. Okay, let's go forward. But this example verifies that the say in degree is not everything. So we have 8 nodes. This is the same example as what we have used before. So if you calculate the stationary density by solving the say set of linear equations, which is actually say the left eigenvector of the eigenvalue 1 of say this T matrix, and this is the result. So by convention, so the sum of these numbers are normalized to be 1, because this is density, right? If you look at this, say, in degree, this is number, the network is assumed to be not weighted, unweighted. And if we rely on this estimate, and if we suppose, which is not the case, but which is not accurate, but if we suppose that the say stationary density is proportional to the in degree, as I have derived in the previous slide, then the stationary density would be this. Again, the summation is equal to unity. And if we suppose that the say stationary density is proportional to the out degree, which doesn't make any logical sense, but let me just try this. And again, the stationary density estimate would be this. If we compare these 3 numbers, let's say this number is very close to this one, not the same though. And this number is more or less close to this one. Wow. But if you compare other, say, the nodes, the stationary density at other nodes, this is very far, more than 3 times different, I think. And this is again, right? So this in actual networks, the correct solution is that this node 6 has a large stationary density, but if you try to estimate the stationary density only based on the in degree, this same node X is estimated to have not a very large in degree, right? But it says that these nodes 1 and 8 would have a very, very large the stationary density, but it's not the case. Of course, it's relatively large, but it's not the largest. If you look at the say out degree, it doesn't make any sense mostly. So it says this is the most central, so it absorbs most of the say the random walkers with this probability, but the actual number is small. So this is a very small example. Just highlights the difference between in degree and the stationary density of discrete time random walks on directed networks. But as I'm iterating, in the case of undirected networks, these 3 quantities all coincide with each other. There will be no difference between in and out degree. and say degree perfectly say is the answer. The degree is the perfect answer to the question of say stationary density of random walks in undirected networks. Okay, good. Let's go to the relaxation time. This is where the spectral things are very important. So this is this lecture is say devoted to spectral theory. So I think it's very important to know, say mention this. So the strategy, how shall we analyze this? The strategy is to say project this say density of random walkers at time n on an approximate basis. So we use the power of the linear algebra to do something similar to Fourier transform on mode expansion. So let's say in the case of say linear algebra, if you are given the matrix, you can say find, so let's say n eigenvalues and corresponding n eigenvectors in terms of which we can represent the same matrix. In this way, we can decompose the matrix and also the say, let's say vector in terms of say the eigenvalues, eigenmodes. This is a strategy we are going to do, to use, I mean essentially. So in sometimes this is called the graphs Fourier transform. Okay. Okay, let's assume undirected networks only in this lecture for simplicity. So the first thing to note is that the transition probability matrix is asymmetric. We have seen this, so sorry for going back to the slide, but let me do this. Dare to do this to show the example. It's instant, you understand this. Where is it? Yeah, this one. So if you look at this amenity matrix, it is not symmetric at all, right? So even though the original JC matrix was symmetric, but if you introduce the this weighting, let's say here's 1/3, but here's 1. What else? Okay, this is sorry. This is it's a directed network, so of course it's non-direct. Okay, so let me do the otherwise. Sorry, we'll mess. Even if the network is symmetric, let's say, let me improvise an example. Okay, I got example, I think. There are 3 nodes. But the transition matrix, if we construct it from here, is this. This is asymmetric, right? So if you look at here and here, it's not symmetric. So as I said, so the analysis of asymmetric matrices is usually more difficult than the analysis of symmetric matrices. But the thing we are going to exploit here is that the transition probability matrix, a special type of asymmetry matrix. So it has a special form. So to exploit this special form, we start by considering this particular symmetric matrix, which has not directly to do with the random walk, at least apparently, right? And start by analyzing this matrix by matrix algebra. Okay, it has a decomposition. This is a symmetric matrix because this part is also symmetric. And we decompose this in this way. So this is always something we can do for the symmetric matrix. And lambda is the eigenvalue. Okay, we can say, okay. So this UL is a corresponding normalized eigenvector. For example, so let's say if I take, say, the multiply this from the right, okay, what we would have is ULT U1, right? So this is row vector, column vector, and this is this transposition, so it's a row vector, right? And then this is simply the inner product. But because of this condition which we impose, and we can do this, so this term survives only, this is a Kronecker delta, so index is the same, 1, otherwise 0. So this term survives only when L is equal to 1. So we have this. And this is the inner product and is equal to 1. So we have recovered this one. Okay, this is value equation where the eigenvector is u1 and the eigenvalue is lambda 1. Okay, fine. And so this is the composition is fine. And this particular matrix is similar to the transition probability matrix T. Similar is a mathematical relationship in say which you'd learn in say linear algebra, defined by this. If the two matrices are similar, then they have same eigenvalues, and their eigenvectors are related to each other. So this is why we studied this particular this matrix. Okay. So this is something we can easily verify, because we have this here, but it's a bit behind the star across. So let me do this myself. This is a ij tilde. If I multiply si on the denominator and this square root sj on the numerator and square root si on the denominator, then they cancel out and this becomes si. So we got si aij. So here I am assuming the undirected network, so I'm not distinguishing between the si and sj. Si out and the in. Okay, this is transition matrix, so fine. So this translates into this. Okay, I have a typo here, so this should be SS. Okay. So this is a diagonal matrix having this component. So let's say d to the minus half it's square root 1 over square root and s1, etc. 1 over square root sn, right? And all 0. So you can verify this. Okay, so I have derived, or at least I have represented tilde in terms of the eigenvalues. And now we can safely say that the T has the same eigenvalues. So because this is a symmetric matrix, right? So the T has symmetric eigenvalues. Symmetric matrix. So they haven't say the real eigenvalues. So the T also is asymmetric, but because of this symmetry relationship with symmetric the matrix, we have found that this transition probability matrix has all the eigenvalues real valued. Okay, and what are the eigenvectors? Okay, so this is a general linear algebra. So if we can link two matrices in a similarity relationship like this, so we can verify that the eigenvectors are given by this. So A tilde is symmetric, so its left and right eigenvalues are the same. So the nth eigenvector of A tilde is denoted by UL, right? And then, but the T, matrix T, it's not symmetric. So even though the its eigenvalues are all real, if I take one real eigenvalue, the corresponding eigenvectors, left eigenvector and right eigenvector, may be different. Actually, you have already seen this case in general. Well, I haven't seen it explicitly, but say, okay, so left eigenvector of T correspond to lambda equal to 1, what's the stationary density, whereas the eigenvector correspond to the same eigenvalue, right eigenvalue vector was this one, all one vector. So they are usually different. Okay. So they are different, but we can find this in this way. Okay. So once we know the eigenvector of the A tilde, we can calculate all the eigenvectors of the T, which is very convenient. Why this is convenient? So if we know the one use of the linear algebra, one use of the eigenvector and eigenvalues is to handily calculate the power of the matrix, right? So we need the power of the matrix, let's say T to the n, because we want to know the behavior of the random walk. So we have shown that they say, okay, the random walk's evolution is governed by this equation, right? So we need the power of the transition property matrix. So, well, if we know this representation and also similarity relationship between, say, T and tilde A, we can easily do this. Okay, T, it's d to the minus half tilde A, and d to the half, right? So if we multiply this twice, okay, this is the first T, and second T is this, right? And they cancel out to become an identity matrix. And here there are two A tildes. Okay, we got something useful. So if we repeat this, we get this. And we know how to calculate tilde A to the power of n, because we have already had an eigenvector, eigenvalue representation. Okay, so this is this. So we just have to multiply take the power of the eigenvector value without manipulating the eigenvector to get this. Okay, if we bit the slide is getting a bit crowding, so this, okay, let's use this different color bit. Okay, these two altogether constitute a right eigenvector, and these two combined constitute left eigenvector. So this is the representation. Okay, so we wanted to know this one. To this end, we need to say the power of this transition probability matrix, whose representation is this. Okay. And okay, so if we do this, we get this. What does it mean? Okay, this is a right eigenvector, so this is basically, let's say, vertical vector, and this is the horizontal, right? And then the P0 is essentially, so intuitively, it's a horizontal vector. And if you just plug this in here, so we take the inner product of this one and this one, which is now moved here. This is scalar, and this is the the horizontal row vector, as well as this one. This is the situation. So if you look at each individual element of this equation, so we can discover where random walker is visiting after n steps, right? So this. Okay, this we have introduced further notation. A bit notation is getting heavier, but we are just reading off the ith row from this equation, right? So the A summarizes this part, these parts, right? And in this way, so this is called graph Fourier transform essentially. So if we have, say, the density of random walkers at different nodes at time n, so we can represent it in terms of, say, this. So this is a very useful quantity, because this is something we can calculate. Well, if we increase time by 1, we just change this part in this way. So different modes, different eigenvalues define different modes. This is a mode decomposition. So this is like, say, Fourier mode. So now the mode is defined by, say, each eigenvalue, let's say lambda n or lambda r1, sorry. And if it's like a Fourier mode. So the k, difference in k, it's something I say difference in lambda I. So we have n modes. So this, yeah, as I said, this winter school is for the spectra, right? Spectral theory. So this, yeah, that's why I'm spending a bit time on this. So this graph spectral, the T has the following property. First, so I'm not proving any of this. First, the eigenvalues, all the eigenvalues are between -1 and 1. Second, so okay, so let me flip the order. Okay, this I explained. And there is one eigenvalue, so which corresponds to the stationary density. That's something we have covered, right? We sort of happen to find a one eigenvalue of 1. I mean, it is 1 equal to 1. And the associated left eigenvector and right eigenvector. And -1 is very exceptional. So -1, say if, the eigenvalue -1 would mean that the Walker is flipped between two parts. The bipartite graph case. So if there are two parts, and if there is no connection within each part, then what the round Walker can do is to iterate between this, let's say, A part and B part. So if Walker is initially here, there is no way for the Walker to come back to A part in odd times. In the first step, it has to go to some node in B part, let's say here or here. And in the even steps, in the next step, let's say step 2, it has to come back to part A, whichever node, including the starting point. So in this way, so the even times, the Walker is visiting part A, and in odd times, the Walker is visiting B. So there is no notion of stationary density. So stationary density means that the Walker's density approaches a certain density as time goes to infinity, regardless of whether the time is even or odd. But in this representation, it is impossible. So if you look only at the even times, I mean, Walker's density would approach to a certain one. But in odd times, the Walker's density in the A part becomes 0. So there is no stationary density. So this is exceptional case. So there is no convergence. But otherwise, if this is not the case, if the network is connected, then we all have this. And this one as a network, the one eigenvalue 1 is unique if the network is connected. The network is connected, then this one eigenvalue is unique. Otherwise, if the network has 3 components, there are 3 one eigenvalues. But let's forget about this case, and let's focus on the case that the network is connected. And then this is the equation we have found. And I have stated around here the properties of the eigenvalues. And we have one eigenvalue, which is here. But otherwise, what governs the relaxation is this one. Okay. So if we have the largest, so by definition, this is the second largest eigenvalue in modulus. So if let's say we have the 0.9 minus 9 and 0.8 minus 0.9, we say that this is larger in modulus in absolute value because all the eigenvalues are real. So anyways, so this is the second largest eigenvalue in terms of absolute value. So because we are considering lambda to the n, so if lambda is small, then this decays first as compared to this case, right? So of course, we say you have several other terms, n minus 2 terms, other terms, but the governing the many time scale is defined by this. Relaxation time scale is governed by this. So if the second eigenvalue, which is its difference from say the largest eigenvalue, which is 1, is called the spectral gap, it's small, then it means that the second eigenvalue is very close to 1. Then the relaxation to the stationary density represented by this term would be very, very slow. But if the all eigenvalues, and hence the second largest eigenvalue in the modulus, is very small, let's say like 0.1, then as we iterate the random walks moving process, then the remainder part, like a second term or other terms, will decay to 0 very rapidly. So in this case, we say that this relaxation is fast. So yeah, because this is this, and because they say if we have this, what's this? This is the right eigenvector, and this is the left eigenvector, and this is stationary density essentially. Normalize to respect the, hopefully you remember this one. So this is normalization condition. So we normalize them in this vector in a slightly different way than before, like this, but it's not essential. What is important is this part. Old one, or the node strength. Node strength is proportional to the stationary density. So if you use this, it say helps us to say simplify this part, which becomes the stationary density. So yes, the Walker's density approaches the stationary density, and this is the relaxation part, main relaxation part. Okay, and as I said, this difference is often called the spectral gap, and the Perron-Frobenius theorem, so-called. So this will be covered by say different lectures. I won't explain really, but guarantees that this is for this largest eigenvalue and eigenvector, which is 1. So the matrix is all non-negative elements, and if we iterate the matrix, it would have one element 1 in say or ij if n is appropriately large. So anyway, so this is a transition probability matrix for the connected network satisfies the condition for the Perron-Frobenius theorem, so-called. So which guarantees that they say all elements of the eigenvalues, largest eigenvalues, both left and right, are positive. Is it case? Yes. This is all 1, so it's all positive, and it's all they say node strength, number of edges, so it's positive. If number of edges is 0 for some node I, so this will be isolated, right? But it would mean that the network is not connected. Network being connected means that all the nodes are connected in one component. So we can find the path from anywhere to anywhere. But if the node I is isolated, so we cannot reach this particular node from anywhere, right? So it's not the case. So it means that they say we have say a degree, weighted degree, larger than 0. It is connected somewhere even with a very thin edge. Okay, so this is relevant. I mean, Perron-Frobenius theorem can be sort of verified from this. So we have learned that this is, I mean, the second largest eigenvalue, its modulus is important, and the deep mathematical theory which is useful to understand this is a Chiesa constant, so-called. What does it say? So there are different formulations of the Chiesa constant, and here I'm mentioning just one version. So this is a H called this Chiesa constant, and this is the, okay, to define this quantity, so we consider network as usual and partition it into two subsets of nodes. So each set contains nodes. Okay. So this volume, what is this? So okay, this volume is defined by this. So weighted degree of nodes contained in each part summed over the part. Okay. Anyways, so the numerator is more intuitive. So the number of edges that connect these two parts. So normalized in that some way. So if they say one part is extremely small, let's say, so then of course there's a few edges. So in this way, so it's a fair comparison can't be made. So this denominator part sort of normalizes for this fact. So if one part is very small as compared to the other, this denominator becomes small. So it discounts the fact that the numerator becomes small. So in this way, so we are basically looking for the minimum cut. So how can we find a partition between the S and say bar, the say complement, such that there are as few edges as possible between the two parts. So if the network looks like this, yes, this is nice. So there's one edge connecting two parts. So we hoping to find this. Well, of course, the network can't really, they say random, say we can't find such an cut. So Cheeja inequalities bounds the second, say this eigenvalue, right, this, okay. So if the Cheeja constant is small, this is H small case, right? Then this number would be small. So lambda 2 would be equal to 1, let's say, very close to 1. If this is the case, then the relaxation as defined by the previous slide would be very slow. It is intuitive because, I mean, this small Cheeja constant corresponds to this sort of structure called community structure. So if this is the case, I mean, random walk will be confined in one community before discovering and exploring the other community, because there's only one bridge between two communities. So if the network has such an say situation, so the relaxation becomes very slow, right? That's what I have stated here. Okay. So the continuous time random walks on networks. Okay, this is what I've shown for the one-dimensional figure. So I just want to highlight two different notions of random walkers called node-centric versus edge-centric random walks. So they are defined as follows. So in the node-centric one, walker has a clock. So the walker at node I waits for some time, distributed according to a certain distribution. If this is Poisson, this is the say usual say the random walk in continuous time, and it moves to I mean, so it's similar to the continuous time random walk which I stated for the case of say one-dimensional case, and it moves to out neighbor J with probability this one. This is a case similar to the case of the say discrete time random walk. As edge-centric random walk, what is this? So each edge, not node, incident to the I is activated with inter-event time distribution this, and the walker moves to the first activated node neighbor. What's the difference? Okay, so in the case of a node-centric random walk, so there are some differences, but here this figure highlights the difference. So if the walker is visiting here, in the next step, the walker goes to one of the neighbors with the say 1/3 probability 1/3, and in this figure it's 1/4. But in this edge-centric case, each edge has a clock. So this number one describes the rate at which random walk escapes from a node. So let's say the time to next event, next jump, obeys and say exponential distribution whose mean is equal to 1. So if there are three temptations for the walker to escape from here at each rate each one, so the walker escapes from this node at a total rate of 3. So it stays on this node with mean time equal to 1/3. Here 1/4. So in the edge-centric case, so the point is that they say the walker would escape the hub, the larger degree nodes with a higher rate, whereas in the node-centric case, it's not the case. No matter which node the walker is visiting, the mean time to stay at a node is equal to 1 in the case of the Poisson process, if this is a Poisson process. If this is non-Poissonian distribution, the situation is much more complicated. That's interesting actually. So then that's something I've spent on studying, say, several things. But say here I'm not focusing on this issue. So to advance and say let's focus on the Poissonian classic one. Okay. So how shall we analyze this? So the master equation, this is a continuous time, so we are discussing how the density evolves, right, in terms of continuous time. So the node-centric case, so this is master equation. So this is escape rate from I to j somewhere, and this is j to I. And okay, so if we write this down, so let's say I is equal to y, this escape, this is a rate at which the walker enters from j to I. Okay, this is a weight, so also the time. So okay, so each walker stays in node I once it visits node I with the mean time equal to 1. So this is how this is minus 1, right? So how the walker's density decreases. Okay, if you look at this, okay, if we define this matrix denoted by say prime, okay, this can be represented by this. So, okay, these are again the same degree matrix. Oops, something missing here, so we should erase this anyways. And then this is called a combinatorial Laplacian matrix. It's a very important matrix. Anyway, this describes the master equation. And if we set this equal to 0, then this is stationary density. And if we set this to 0, okay, so P of t I plus t is equal to 0. So the P, okay, this is a stationary density, so the asterisk. We move, either part to the right hand side, we get this. Okay, we have the same as the discrete time random walk. So if the network is undirected, the stationary density is given by this. Fine. So the other part is the edge-centric continuous time random walk. So its master equation is slightly different, which is this. What does it say? So if you look at the ith element, like before, so this is the diagonal matrix having degree of out. So the minus p si out pit plus aji pjt summed over j, sorry. So this is the incoming. This is outgoing. This is outgoing. I to j. Okay, so if you set this is equal to 0, then we get this. Because L is equal to D minus A by definition. So this is 0 eigenvector, slightly different. But the theory of the Laplacian matrix shows that okay, for undirected networks, okay, this has a 0 eigenvalue, which is this. So we can verify this, but let me skip. Okay. Okay, perhaps I'm spending too much time, so let me skip this particular part. Okay, so this is summary finally. So I'm using a bit too much time, but I've introduced a discrete time random walk and continuous time random walks, and then several important aspects are the transient probability matrix, stationary density, and this is a key result for undirected network where the stationary density is proportional to the node strength, and mode decomposition, which is like a Fourier transform, and relaxation time scale is governed by the second largest eigenvalue in modulus. And I relatively quickly went through the continuous time random walks. So we have to, networks have to distinguish case between node-centric and edge-centric random walks, having a respective, different types of Laplacian matrices. And I also highlighted explicitly and implicitly on the difference between this undirected networks and direct networks. So this is much more difficult, and this is manageable even for weighted networks. Okay, let's conclude my lecture here, and see you in the second lecture.